Everything you think you know about space and time might be wrong. Not in the sense that your everyday experience is mistaken, but in a deeper sense, a sense that touches the foundations of physics itself. For over a century, space-time has served as the stage on which all physics plays out, and Einstein demonstrated that space and time form a unified fabric that bends and curves wherever matter and energy concentrate. That insight transformed our understanding of gravity, the cosmos, and reality itself. What some of the most prominent theoretical physicists are now suggesting runs counter to a century of thinking. Space-time may not be fundamental at all. 3 dimensions of space and 1 dimension of time, the framework we experience every waking moment, might turn out to be derived quantities rather than basic features of existence. Fringe speculation, this is not. Serious research fills the most respected physics journals, gets presented at major conferences, and occupies physicists at leading institutions worldwide. Juan Maldacena, Nima Arkani-Hamed, then at Susskind, Gerard 't Hooft. These names have shaped theoretical physics for decades, and their work points toward space-time emerging from something deeper. Think of temperature for a moment. Temperature emerges from the motion of atoms, useful and measurable, yet not fundamental. Space-time geometry might work the same way, extraordinarily useful within its domain, but not the bottom layer of reality. By the end of this video, you will grasp why serious physicists pursue this line of research, what evidence supports it, and what frameworks like holography, the ADS-CFT correspondence, and the Amplituhedron actually mean for our understanding of existence at its most basic level. If you find value in explorations like this, in understanding what theoretical physics suggests about reality itself, consider subscribing to the channel, which helps these deep dives reach more curious minds. Now, let us begin. Clarifying what physicists mean when they call something fundamental matters here. Fundamental means appearing in the most basic equations, something that cannot be derived from anything more primitive. Electrons qualify in the Standard Model because nothing smaller composes them. The electromagnetic field qualifies because nothing deeper constructs it. Space-time has held fundamental status for over a century. Einstein's equations describe how matter curves space-time and how that curvature steers matter. With space-time simply there from the start, the arena in which physics unfolds. When physicists now question space-time's fundamental status, they mean something specific. The deepest equations of physics, the ones describing reality at its most basic level, might not contain space-time as a starting ingredient. Space-time would emerge from those equations the way thermodynamic properties emerge from the statistics of particles. Temperature offers the right analogy. You can measure it, predict system behavior from temperature differences, and none of that makes temperature less real. What makes it non-fundamental is that it describes how atoms and molecules move collectively. No temperature exists at the level of individual particles, only positions and momenta. Temperature emerges when many particles combine. Space-time might work similarly. At ordinary scales, space-time seems perfectly real, continuous, fundamental. At the deepest level, the Planck Scale, where quantum effects and gravity both become important, space-time might dissolve into something else, some quantum structure from which familiar geometry emerges as approximation. Calling space-time emergent would not make it illusory, just as temperature is not illusory. Space-time would remain an effective description, extraordinarily useful within its domain, just not the final word on reality. Appreciating why emergent space-time represents such a revolutionary idea requires understanding how central space-time has become to physics since Einstein. Before Einstein's work, space and time existed separately, with space serving as where things existed and time serving as when things happened, two independent containers for physics to fill. Special relativity in 1905 fused them into a single four-dimensional structure, and suddenly distances in space and durations in time depended on the observer's motion. What one observer measured as purely spatial separation, another measured as combined spatial and temporal separation. General relativity arrived in 1915 and pushed even further. Space-time became dynamic, responding to mass and energy by curving, and that curvature determined how objects moved. Gravity vanished as a force pulling objects through space, and reappeared as space-time curvature itself. For a century now, this framework has dominated fundamental physics. Quantum field theory places particles and fields on space-time. Cosmology describes space-time evolution, and black holes represent extreme space-time configurations. Every experimental prediction operates within the space-time framework. Einstein's equations treat space-time geometry as a dynamical variable, something responding to matter and energy, yet still a fundamental ingredient put in by hand as the arena for physics. Emergent space-time proposals challenge precisely this assumption. Space-time geometry becomes an output rather than an ingredient, with something deeper, perhaps quantum information or abstract geometric structures, giving rise to space-time as effective description. A concept that seemed fundamental would reveal itself as derivative, the stage turning out to be part of the play itself, emerging from the script rather than preceding it. Tracing how understanding of space and time has evolved reveals that humans have revised these concepts before. Isaac Newton published his Principia in 1687, laying out laws of motion and gravitation that dominated physics for 2 centuries. Newtonian space stood absolute and fixed, with time flowing uniformly everywhere, unaffected by anything happening within it. Gravity in Newton's conception acted instantaneously at a distance, the Earth pulling on the Moon across the void of space with no delay. Newton himself found this absurd and famously admitted he could not explain how gravity actually propagated. That framework worked extraordinarily well for over 200 years, predicting planetary motions, cannonball trajectories, and tidal behavior, while enabling the Industrial Revolution and space exploration. Albert Einstein's 1905 paper on special relativity reframed everything. Space and time unified into space-time, a single four-dimensional structure where the constant speed of light meant measurements of time and space depended on relative motion. Two observers moving relative to each other disagreed about simultaneity, object lengths, and process durations. General relativity arrived 10 years later as an even more radical revision. Gravity ceased being a force and became space-time curvature, with mass and energy causing space-time to curve, so objects moving through curved space-time followed paths appearing as gravitational attraction. Einstein's space-time was no passive stage, but a dynamic participant that could bend, stretch, warp, and form singular points at black hole centers. Space-time geometry became the fundamental quantity determining how matter moved. For a century, this remained the dominant framework, with space-time fundamental and everything else happening within it. What some physicists now ask is whether even Einstein's space-time represents the final answer. The first hint that space-time might not be fundamental emerges from thinking carefully about very small scales. Scales so tiny they challenge the concept of distance itself. Planck Scale marks where this happens, a set of natural units constructed from three fundamental constants: the speed of light, Planck's constant from quantum mechanics, and Newton's gravitational constant. Combining these constants yields units of length, time, and mass, marking where quantum effects and gravitational effects both matter simultaneously. Approximately 1.616 times 10 to the negative 35 meters defines the Planck length, roughly 6.36 times 10 to the negative 34 inches. Appreciating that smallness requires comparison. A proton measures about 10 to the negative 15 meters in diameter, which makes the Planck length 20 orders of magnitude smaller still. Scaling a proton up to the size of the observable universe would scale the Planck length up to roughly proton size. Planck time clocks in at approximately 5.391 times 10 to the negative 44 seconds. The interval light needs to traverse 1 Planck length. Planck mass measures approximately 2.176 times 10 to the negative 8 kilograms, about 4.80 times 10 to the negative 8 pounds, roughly matching a small grain of sand. These scales mark where current theories break down, where both quantum field theory and general relativity have been tested extensively, but never together, never in regimes where both matter equally. Here is where things get strange. Imagine trying to measure distances smaller than the Planck length, which would require particles with extremely high energies, since quantum mechanics links higher energy to shorter wavelength, and shorter wavelength allows finer resolution. Concentrating enough energy into a small enough region creates a black hole, and that's the problem. Gravitational effects of the energy itself grow so strong that the region collapses behind an event horizon, with the very act of measurement preventing the measurement from succeeding. Distance as a concept might lose operational meaning below the Planck scale, because no experiment, even in principle, can probe separations smaller than the Planck length. The measurement barrier argument reveals something profound about physical concepts and their limits. Suppose you want to measure a particle's position very precisely, which in quantum mechanics means The uncertainty principle relates position precision to momentum uncertainty, with knowing position precisely meaning knowing momentum imprecisely. Localizing a particle to a small region requires short wavelength probes, and short wavelength means high frequency, which in quantum mechanics means high energy, since photon energy scales proportionally with frequency. Particle accelerators need enormous energies precisely for this reason. Seeing atomic nucleus structure requires giga-electron-volt particles, and smaller scales demand even higher energies. Energy gravitates, which creates the fundamental problem. Concentrating enough energy to probe distances smaller than the Planck length generates a gravitational field strong enough to form a black hole, with the event horizon blocking access to the scale you tried to measure. Planck scale energy, concentrated into a Planck-sized region, produces a horizon with Planck length radius. No technological solution exists because this limitation stems not from instrument quality, but from quantum mechanics and gravity combining. The concept of distance, requiring the ability to measure separations, loses operational meaning below the Planck scale. If measuring distances below the Planck length proves meaningless, perhaps distances below that scale simply do not exist. Spacetime might be discrete at that scale, or something entirely different might take over, which provides one motivation for thinking spacetime might not be fundamental. Feeling the numbers helps ground these abstract concepts. So consider the hierarchy of length scales in nature. Human bodies measure roughly 1 to 2 meters. Bacteria span a few micrometers, representing a million-fold reduction. Atoms measure about an angstrom, representing another 10,000-fold reduction. And atomic nuclei span about a femtometer, representing yet another 100,000-fold reduction. 15 orders of magnitude separate human scale from nuclear scale, with each step down revealing new physics, biology giving way to chemistry, giving way to atomic physics, giving way to nuclear physics, with different concepts becoming relevant at each scale. Planck length sits another 20 orders of magnitude below nuclear scale, meaning the step from nuclear to Planck exceeds the step from human to nuclear. Journeying from familiar scales to Planck scale crosses 35 orders of magnitude. Each historical step down changed the character of physics. But what physics looks like at Planck scale, where emergent space-time ideas become relevant, remains unknown. Theoretical frameworks exist, but direct observation does not. Timescales tell a parallel story. Human heartbeats take about a second. Atomic processes happen in attoseconds, around 10 to the negative 18 seconds. Nuclear processes happen in femtoseconds to attoseconds. And Planck time sits at 10 to the negative 44 seconds, roughly 26 orders of magnitude below atomic timescales. The universe's age of about 14 billion years, or 4 times 10 to the 17 seconds, spans 61 orders of magnitude above Planck time. That range from Planck time to cosmic age is staggering. Energy scales follow similar patterns. Room temperature corresponds to about 0.025 electron volts. Chemical bonds involve a few electron volts. Nuclear physics involves mega electron volts, and Planck energy reaches about 10 to the 19 giga electron volts, or 10 to the 28 electron volts. At Planck energy, gravity becomes as strong as other forces. Quantum gravitational effects become unavoidable, and emergence of space-time, if it occurs, happens around these scales. The second major hint that space-time might not be fundamental arrived from an unexpected direction: black hole thermodynamics. Physicists discovered something remarkable in the 1970s. Black holes behave like thermodynamic systems, possessing temperature, entropy, and energy radiation, which nobody expected, given that black holes were supposed to represent ultimate simplicity, regions where space-time curved so severely nothing could escape. Jacob Bekenstein proposed in 1973 that black holes possess entropy, measuring how much information they contain. That claim was bold, since entropy usually relates to counting microscopic arrangements producing the same macroscopic state, with gases having high entropy because many atomic arrangements produce identical pressure and temperature. What microscopic arrangements could exist inside a black hole? Bekenstein's insight was that black hole entropy scales proportionally with event horizon area, not volume. Ordinary systems show entropy scaling with volume. Doubling gas container volume roughly doubles entropy because twice as many atoms fit in twice as many arrangements. Black holes work differently. Doubling horizon area doubles entropy, encoding information content on the surface rather than throughout the interior. Stephen Hawking showed shortly after Bekenstein's proposal that black holes radiate energy with thermal spectrum, and this Hawking radiation has temperature inversely proportional to black hole mass. That radiation carries entropy away, confirming black holes as genuine thermodynamic objects. The Bekenstein-Hawking entropy formula emerged as elegant. Entropy equals horizon area divided by 4 times Planck length squared, multiplied by Boltzmann's constant. Planck units simplify this to 1/4 of area measured in Planck areas. Perspective helps here. Consider a surface with 1 square meter area, about 10.76 square feet. Using the Bekenstein-Hawking formula, adapted for flat surfaces, information capacity works out to roughly 1.38 times 10 to the 69 bits, roughly 1.28 times 10 to the 68 bits per square foot. These numbers do not suggest building memory cards at this density. They illustrate a scaling principle. Information in gravitating systems scales with area rather than volume. That principle planted the seed for what became the holographic principle. How Bekenstein came to propose black hole entropy reveals why entropy must scale with area. During the early 1970s, Bekenstein was a Princeton graduate student working with John Wheeler, who had coined the term black hole and pioneered gravitational physics. Classical thermodynamics has a second law. Entropy never decreases in closed systems. Entropy measures disorder, the count of microscopic arrangements consistent with a given macroscopic state. And the second law says systems evolve toward higher entropy, more disordered states. Bekenstein spotted a problem. Throwing something with entropy into a black hole makes that thing disappear behind the horizon, decreasing visible universe entropy. Does this violate the second law? Preserving the second law required proposing that black holes themselves possess entropy. So throwing something in increases black hole entropy, keeping total universal entropy from decreasing. Determining how much entropy a black hole has required reasoning from its properties, and simple black holes have only mass as a macroscopic property, which determines horizon size. Through a thought experiment involving lowering radiation boxes into black holes, Bekenstein argued entropy should scale proportionally with event horizon area, rather than enclosed volume. Doubling a black hole's mass would quadruple its horizon area and quadruple its entropy. Hawking initially resisted Bekenstein's idea because entropy implies temperature, and temperature implies radiation. But nothing escapes a black hole. Calculating quantum mechanics effects near the horizon changed Hawking's view, revealing that black holes do radiate, do have temperature, and Bekenstein was right. The Bekenstein-Hawking entropy formula became one of theoretical physics' most important results, establishing that gravitating systems encode information proportionally with area, planting holography's seed. Area scaling of black hole entropy led to a profound proposal, the holographic principle. Gerard 't Hooft, a physics Nobel laureate, proposed in 1993 that physics might undergo dimensional reduction at fundamental scales. Information needed to describe a three-dimensional region might be encodable on a two-dimensional surface surrounding that region. Leonard Susskind developed these ideas further, coining the phrase that we might inhabit a holographic universe, meaning three-dimensional reality might be encoded on a two-dimensional surface. That sounds mystical, but concrete physics underlies it. Maximum information fitting inside a spatial region scales proportionally not with volume, but with boundary area. Attempting to pack more information than the boundary can encode leads to gravitational collapse, producing a black hole, with exactly the maximum entropy its horizon area allows. What this means for space itself is striking. Ordinary intuition gives space three dimensions: left, right, forward, backward, up, down. Each point in three-dimensional space can hold information independently, so total information capacity should scale with volume. The holographic principle says this intuition fails at the deepest level. Fundamental information capacity scales with area, making the third dimension, the direction perpendicular to any surface, somehow redundant, reconstructible from boundary data. Three dimensions do not become illusion, since you can clearly move through them. What the principle means is that three-dimensional description might be equivalent to a lower dimensional description, with bulk physics encodable without loss on a two-dimensional surface. If true, space-time as we perceive it is not the fundamental description. Fundamental description lives on a lower dimensional boundary, with bulk space-time emerging from boundary physics. This was theoretical speculation in the 1990s. What physicists lacked was A concrete example, a specific model where the holographic principle could be tested mathematically, where both bulk and boundary descriptions existed and could be compared. That example arrived in 1997. Juan Maldacena, then a young Harvard physicist, proposed in 1997 what became known as the ADS-CFT correspondence, arguably theoretical physics' most important development in the past quarter century. The correspondence proposes exact equivalence, a duality, between two very different theories. On one side sits a gravitational theory, specifically string theory, living in anti-de Sitter space, or ADS, a space-time with negative curvature like a saddle shape extended to higher dimensions, possessing a boundary at infinity. On the other side sits a conformal field theory, a quantum field theory with special symmetry properties, living on that anti-de Sitter boundary. That boundary has one fewer dimension than the bulk. 5-dimensional bulk corresponds to 4-dimensional boundary. 4-dimensional bulk corresponds to 3-dimensional boundary. The correspondence claims these two theories are equivalent, with every bulk calculation having a corresponding boundary calculation. Every state in one theory corresponding to a state in the other. They are the same theory written in two languages. This makes the holographic principle concrete. Bulk spacetime, with all its dimensions and gravitational dynamics, encodes on a lower dimensional boundary possessing no gravity at all. Gravity in the bulk emerges from non-gravitational dynamics on the boundary. Staggering implications follow. The boundary theory contains no space-time in the bulk sense, just quantum fields on a fixed background. Yet, from correlations and dynamics of these boundary fields, an entire extra spatial dimension emerges, complete with gravity, black holes, and geometric curvature. Space-time in this correspondence is not fundamental, it is derived. It emerges from the boundary theory. Careful qualification matters here. The ADS-CFT correspondence does not directly model our universe, which does not appear to be anti-de Sitter space. Our universe has positive cosmological constant and is expanding, not the negative curvature and specific structure of ADS. Applying these ideas to realistic cosmology remains active and difficult research. What ADS-CFT provides is a theoretical laboratory, a controlled setting where space-time emergence can be studied precisely. And in that laboratory, space-time definitely emerges. Maldacena's 1997 discovery of ADS-CFT marks one of those pivotal physics moments where everything shifts. Studying string theory, specifically low-energy behavior of configurations called D-branes, surfaces where open strings can end, Maldacena noticed that stacking many D-branes together produced interesting physics. From one perspective, the stack looked like a quantum field theory, a gauge theory living on the brane surface. From another perspective, branes curved space-time around them, creating geometry resembling anti-de Sitter space near the branes. Maldacena proposed these perspectives were not just similar, but exactly equivalent. The gauge theory on the branes was the same theory as string theory in the curved space-time around them. That was the ADS-CFT correspondence. The proposal was radical. A gravitational theory, where space-time dynamically curves and responds to matter, was claimed equivalent to a non-gravitational theory where space-time remained fixed and non-dynamical. How could a gravitational theory equal a non-gravitational one? Dimensions provided the answer. The gravitational theory possesses more spatial dimensions than the non-gravitational theory, with the gauge theory living on a lower dimensional boundary. The bulk dimension with gravity emerges from boundary physics without gravity. Maldacena's paper became the most cited in theoretical high-energy physics, with thousands of subsequent papers exploring and extending the correspondence. Countless limit checks, where both sides permit calculation, have all confirmed the equivalence. Mathematical proof ADS-CFT lacks, but overwhelming evidence supports it. The correspondence stands as one of the strongest pieces of evidence that space-time can emerge from more fundamental structures. What Maldacena demonstrated is that space-time emergence is not just possible in principle, but realized in a concrete, calculable example. Bulk space-time with gravity exactly equals boundary physics without gravity. Space-time emerges. Two physicists named Shinsei Ryu and Tadashi Takayanagi discovered something in 2006 that deepened understanding of how geometry emerges from quantum information. Their Ryu-Takayanagi formula connects two quantities that seem utterly unrelated. Entanglement entropy exists on the boundary side. Entanglement is a quantum phenomenon where states of different system parts correlate in ways having no classical analog, and measuring one entangled system instantly affects what you know about the other, regardless of distance. Entanglement entropy measures how much entanglement exists between a region and its complement. Divide a quantum system into region A and everything else, and entanglement entropy tells you how correlated region A is with the rest. Minimal surfaces exist on the bulk side. In ADS-CFT, the bulk is curved spacetime, and a minimal surface is the surface of smallest area spanning a given boundary. The Ryu-Takayanagi formula says these quantities are equal. Entanglement entropy of a boundary region equals the area of the bulk minimal surface ending on that region's boundary, divided by 4 times Newton's gravitational constant. When I first encountered this idea, reading it several times became necessary. Entanglement entropy is purely a quantum information quantity, discussing correlations between quantum states with nothing obvious connecting it to geometry. Minimal surface area is purely geometric quantity, discussing space-time shape, distances, and curvature, with nothing obvious connecting it to quantum information. Yet, in ADS-CFT, they are the same thing. Bulk space-time geometry, specifically minimal surface areas, is determined by boundary theory entanglement structure. Geometry itself might be built from entanglement. Distance between two bulk points might be determined by how quantum information organizes on the boundary. Space is not a container, but a reflection of quantum correlations. Mark van Raamsdonk pushed the entanglement geometry connection even further in 2010 and 2011. arguing that entanglement is not just related to geometry, but might be what holds space-time together. Consider a thought experiment within ADS-CFT. Take the boundary theory and divide it into two parts. High entanglement between these parts means connected bulk spacetime, with smooth geometry linking regions corresponding to each boundary part. Now imagine reducing entanglement between the two boundary parts. Van Ramstonk argued that reducing entanglement stretches the bulk geometry, making the connection between regions longer and more tenuous. Removing all entanglement, making the two boundary parts completely uncorrelated, tears the bulk geometry apart, with space-time pinching off into two disconnected pieces. Pause and consider what this means. Space-time connectivity, whether two regions are geometrically connected or separated, depends on quantum entanglement. Space is not a pre-existing stage, but woven from threads of quantum correlation. This is a conceptual model developed within ADS-CFT's specific setting, not a proven feature of all physics. What it suggests is a profound shift in thinking about space. Instead of asking how objects move through space, we might need to ask how entanglement patterns give rise to the illusion of space in the first place. Van Ramstonk illustrated this with an analogy. Imagine reconstructing a three-dimensional shape from correlations in a two-dimensional dataset. Bulk geometry in this view is like that reconstructed shape, derived from the pattern of correlations in boundary theory rather than existing as a fundamental entity. If geometry comes from entanglement, then familiar distances and separations we experience are not primary reality features, but derived quantities, bookkeeping for something more fundamental, the structure of quantum information. Locality is one of the concepts that emergent spacetime research challenges most directly. In physics, locality means interactions happen at specific points, with two particles interacting when they meet at the same location. Causes producing effects where causes are located, and effects propagating outward at most at light speed. Locality is deeply embedded in physics formulation. Quantum field theory puts interactions at space-time points. Differential equations describe field changes from point to neighboring point, and the entire mathematical framework assumes local physics. Quantum mechanics makes locality puzzling, though. Entangled particles exhibit correlations seeming to defy locality, with measuring one particle instantly correlating with what measuring the other finds, regardless of separation. Einstein called this spooky action at a distance. These correlations do not violate locality in the sense of sending faster-than-light signals. Entanglement cannot enable instantaneous communication, since correlations only become apparent when comparing measurements, which requires ordinary communication. The correlations themselves just seem non-local. In emergent space-time scenarios, this puzzle dissolves. If space-time is emergent, locality is emergent, and the concept of distance, of things being far apart, becomes derived rather than fundamental. Entanglement correlations are not spooky action at a distance, because at the fundamental level there is no distance. Distance emerges from the pattern of correlations, not the other way around. If locality is emergent, non-local features of quantum mechanics are not bugs, but clues to the underlying structure from which local space-time emerges. Juan Maldacena and Leonard Susskind proposed a conjecture in 2013, capturing the entanglement geometry connection in a striking slogan. ER equals EPR. ER refers to Einstein-Rosen bridges, better known as wormholes, theoretical tunnels through space-time connecting distant regions. Einstein and collaborator Nathan Rosen discovered them as general relativity solutions in 1935, though actually traversing one remains science fiction. EPR refers to Einstein-Podolsky-Rosen correlations, the quantum entanglement that Einstein himself found disturbing. In 1935, the same year as the wormhole paper, Einstein, Podolsky and Rosen published a paper arguing quantum mechanics must be incomplete because it seemed to require spooky action at a distance between entangled particles. The ER equals EPR conjecture proposes these two 1935 discoveries are actually the same phenomenon viewed from different perspectives. Entangled particles connect via microscopic wormholes, with quantum correlation between distant particles being a geometric connection through space-time, a tunnel too small and non-traversable to send signals through, but a connection nonetheless. If this conjecture is correct, entanglement is not just related to geometry. Entanglement is geometry. Every entangled particle pair shares a tiny wormhole, every quantum correlation corresponding to a spatial connection. This would unify two of physics' strangest features. Entanglement, the quantum phenomenon Einstein found disturbing, would be explained by wormholes, the geometric phenomenon Einstein discovered. Spooky action at a distance would not be action at a distance at all, but action through an extremely short geometric shortcut. Clarity matters here. ER equals EPR is a conjecture, not an established result. It serves as a conceptual tool in discussions of black holes, quantum information, and space-time structure, providing a way to think about how geometry and quantum mechanics might unify. Proof has not arrived, and precise formulation and validity domain remain active research subjects. What the conjecture illustrates, even if not literally true in all cases, is how deeply geometry and quantum information seem intertwined. The idea that space-time might emerge from entanglement rather than entanglement occurring within space-time is taken seriously by leading researchers. Wormholes play a central role in the ER equals EPR conjecture, so understanding them matters. A wormhole, or Einstein-Rosen bridge, is a theoretical tunnel connecting two separate space-time regions. In the simplest case, imagine two black holes in distant parts of the universe, with their interiors connected by a throat. Einstein and Rosen discovered this possibility in 1935, the same year Einstein, Podolsky and Rosen published their Quantum Entanglement paper. No connection between these two findings was seen at the time. General relativity wormholes are not traversable, since they pinch off too quickly, with any object entering one end crushed by the collapsing throat before emerging from the other. Non-traversability does not mean physical meaninglessness, though. Wormholes represent a topological space-time feature, a connection between regions that would otherwise be separate. The connection is real, even if you cannot use it for travel. The ER equals EPR conjecture proposes that every entangled particle pair connects via a microscopic wormhole, far too small to traverse, but representing the geometric counterpart of quantum correlation. Creating an entangled pair and moving the particles far apart stretches a tiny wormhole across vast distances. The particles are far apart in ordinary space, but close together through the wormhole. Non-local entanglement correlation has a local geometric explanation through a different route. This perspective suggests space-time connectivity and quantum entanglement are two descriptions of the same phenomenon. Where entanglement exists, geometric connection exists. Where entanglement breaks, geometry disconnects. The conjecture remains unproven, but provides a powerful conceptual tool for thinking about the geometry-quantum mechanics relationship. If correct, quantum entanglement weirdness and space-time structure are intimately linked. The holographic principle and space-time emergence connect closely to the black hole information paradox, one of theoretical physics' most important puzzles. Something falling into a black hole seems to disappear forever. The event horizon is a one-way surface with things falling in but nothing coming out. Whatever information the infalling object carried, its structure, history, and quantum state seems lost behind the horizon. Quantum mechanics requires information preservation, though. Every quantum process must be reversible in principle, with the final state allowing initial state reconstruction. This is called unitarity, one of quantum mechanics' fundamental principles. Hawking radiation complicates the picture. Black holes are not truly black, but radiate energy slowly, losing mass over time, and, given enough time, can evaporate completely. Hawking radiation, as originally calculated, is thermal, though, carrying no information about what fell in, resembling structureless, random heat radiation from a hot object. If Hawking radiation is truly thermal, then black hole evaporation destroys information about what fell in. The final state, thermal radiation, cannot reconstruct the initial state. Unitarity would be violated. This is the black hole information paradox. Either quantum mechanics is wrong about unitarity, general relativity is wrong about black holes, or something more subtle is happening. Holography suggests the subtle resolution. In ADS-CFT, everything happening in the bulk, including black hole formation and evaporation, corresponds to unitary evolution in the boundary theory. Information is never lost, because the boundary theory is quantum mechanical and preserves unitarity. From bulk perspective, information seems lost behind the horizon. From boundary perspective, information is always accessible, encoded in complex correlations among boundary degrees of freedom. Apparent loss is an artifact of using the bulk description where it breaks down. This resolution suggests bulk space-time description is not fundamental. At the deepest level, boundary description applies, and boundary description preserves information perfectly. A completely different line of evidence that space-time might not be fundamental comes not from black holes and entropy, but from particle collision physics. Particles collide, scatter, combine, and produce new particles. And calculating these outcome probabilities is particle physics' bread and butter. For decades, Feynman diagrams have been the standard method. Feynman diagrams pictorially represent particle interactions. A photon travels from here to there. An electron emits a photon and changes direction. Two particles meet at a space-time point, interact, and emerge as different particles. Each diagram represents a possible history, a path through space-time, with total probability coming from summing all possible histories. This approach works, enabling predictions matching experiments to extraordinary precision. What it is built on is space-time locality, the assumption that interactions happen at specific space-time points, and the total answers come from summing all such local interactions. In 2013 and 2014, Nima Arkani-Hamed, one of his generation's most influential theoretical physicists, along with Jaroslav Trinka, introduced something remarkable: the Amplituhedron. The Amplituhedron is a geometric object living not in ordinary space-time, but in abstract mathematical space, with its shape encoding certain particle physics calculation answers. Here is the striking part. Scattering amplitudes, the probabilities for particle collisions, can be computed directly from the Amplituhedron without ever drawing a Feynman diagram, without ever referring to space-time locality, without using traditional local quantum field theory ingredients. The Amplituhedron provides geometry in an abstract space whose canonical form, a mathematical object associated with the shape, gives the scattering amplitude. The answer emerges from pure geometry, bypassing space-time-based reasoning that has dominated particle physics for 70 years. Arkani-Hamed has described this work as suggesting some future fundamental physics formulation may not treat space-time as primary, that key observables might be computed without standard space-time coordinates. Precision about what the Amplituhedron is and is not matters. The Amplituhedron is a specific positive geometry, a shape in abstract mathematical space, whose properties determine scattering amplitudes in a particular quantum field theory called planar n=4 super Yang-Mills theory. This is not the standard model of particle physics, not a description of electrons, quarks, or particles we actually observe. n=4 super Yang-Mills is a highly symmetric cousin of theories describing the real world, possessing supersymmetry and considered in a special limit called the planar limit, where certain simplifications occur. What makes this remarkable is not that space-time can now be abandoned for all physics, because it cannot. The Amplituhedron works in a specific, highly constrained setting. What makes it remarkable is that it works at all. Traditional particle physics starts with space-time, puts particles in it, makes them interact at local points, and sums all possible histories. This approach seems natural because space-time seems fundamental. The Amplituhedron suggests an alternative. You can get the same answers, the same scattering probabilities, from geometry in abstract space having no obvious space-time connection. Locality, the idea that interactions happen at definite points, emerges from the calculation rather than being put in by hand. This resembles discovering you can compute a circle's area not just from pi times radius squared, but from some completely different procedure, never mentioning circles or radii. The same answer emerges from a totally different starting point. The Amplituhedron work has spawned broader research into positive geometries and their associated canonical forms, with these mathematical structures appearing in many contexts beyond the original Amplituhedron, suggesting this way of thinking might be more general than the specific example. Arkani-Hamed has spoken publicly about the possibility that some future physics formulation will not start with spacetime at all. Spacetime, in this view, is like Feynman diagrams, a useful calculation organizing tool, but not the fairly fundamental object. The fundamental object might be geometric in abstract space, with space-time localities emerging as derived properties. This remains a conceptual research direction, not confirmed experimental result, but it represents serious work by serious physicists published in leading journals. A positive geometry is a mathematical structure defined by positivity constraints, describing a space by inequalities rather than equations, with the region satisfying all inequalities defining the geometry. Simple examples help. A two-dimensional triangle can be defined by three inequalities, each saying you are on one side of a line, with the region satisfying all three being the triangle's interior. Positive geometries have associated canonical forms, mathematical objects encoding geometry structure. For the Amplituhedron, the canonical form turns out to be the scattering amplitude you want to compute. Why physical quantities would encode in positive geometries is not entirely understood, but the phenomenon is striking. Scattering amplitudes describing particle collisions have positive structures, with probabilities being positive and certain physical quantity combinations being positive. This positivity might be more fundamental than the space-time description usually producing it. Traditional Feynman diagram calculations do not make final answer positivity obvious. Many terms add up, some positive, some negative, with the final answer happening to be positive because it must be as a probability. But that positivity emerges from cancellations among many terms. The Amplituhedron approach builds positivity in from the start. The geometry is defined by positivity constraints, and the answer is automatically positive because it comes from a positive geometry. Positivity might be a fundamental feature rather than an emergent one. The research program aims to find positive geometries for more and more physical quantities. Extensions are being developed for other theories, other physical observables, and cosmological correlators. The hope is that geometric language might be more fundamental than space-time language currently used. Tensor networks have helped physicists understand how space-time might emerge from quantum information. A tensor network is a mathematical structure built from tensors, essentially multidimensional number arrays, connected according to a network pattern with shared indices contracted to produce a final result. Tensor networks developed in condensed matter physics and quantum information science as efficient ways to represent complex quantum states. Many particle quantum states can require exponentially many numbers to specify, but tensor networks provide compressed representations capturing essential structure without listing every detail. The holography connection became apparent when researchers noticed certain tensor networks have geometric properties matching the ADS-CFT correspondence. Network connection. Patterns mirror bulk space-time geometry. Boundary state entanglement corresponds to network connectivity, which in turn corresponds to bulk geometry. In 2015 and 2016, Pastavsky, Yoshida, Harlow and Preskill showed specific tensor networks could reproduce key holographic duality features. The networks functioned as quantum error-correcting codes, with bulk information recoverable from boundary portions, just as in ADS-CFT. These tensor network models are not exact ADS-CFT descriptions, but simplified toy models capturing certain features. What they do is make geometry emergence vivid and calculable. In tensor network models, bulk geometry is literally constructed from network structure. Distance between two bulk points relates to network connection pattern. Changing the network changes the geometry. No bulk geometry exists apart from the network. Geometry is the network, not something the network inhabits. This gives physical intuition for how space-time might emerge. Fundamental. Degrees of freedom are quantum information units arranged in a network, and network structure determined by entanglement patterns creates effective geometry. Space-time is a way of describing network properties. Clarity about where we stand matters. The idea that space-time is not fundamental is a research program, not an established fact. Evidence supporting this view comes from theoretical frameworks, ADS-CFT, entanglement geometry connections, and the Amplituhedron, that are mathematically rigorous but operate in idealized settings. Experimental confirmation that space-time is emergent does not exist. A complete theory where space-time emerges from something deeper and also describes the real universe does not exist. What exists are strong hints, theoretical models working too well to be coincidences, patterns suggesting deep connections between geometry and quantum information. Several major open questions remain. First, how do these ideas generalize beyond anti-de Sitter space? Our universe is not ADS, possessing positive cosmological constant and expanding. Can holography and emergent spacetime be formulated for de Sitter space, for realistic cosmology? This is active and difficult research. Progress has been made, but no complete answer exists. Second, is there an experimentally accessible signature distinguishing space-time emergence models from other quantum gravity approaches? No consensus exists on what such a test would look like. Effects are expected at the Planck Scale, far beyond current experimental reach. Physicists are creative, though, and unexpected testing routes might emerge. Third, what exactly is space-time emerging from? Entanglement and quantum information are strong candidates. But precise degrees of freedom, fundamental building blocks, remain unclear. Is it some boundary theory's entanglement structure? Is it a structure of positive geometries and amplitudes? Something else entirely? Fourth, how do locality and unitarity emerge? In ordinary physics, locality means interactions happen at points, and unitarity means probabilities add correctly. In emergent spacetime scenarios, these might be derived rather than fundamental properties. Understanding how they emerge is an open challenge. Despite these open questions, the research direction continues attracting some of theoretical physics' most talented practitioners. Tools developed, from ADS-CFT to positive geometries, have proven enormously productive, even apart from foundational space-time questions. One persistent challenge for emergent space-time research is the lack of direct experimental tests. Effects are expected at Planck Scale, 20 orders of magnitude below currently accessible scales. How might these ideas ever be tested? Several possibilities are being explored, though none has produced a definitive test. Cosmological observations might reveal early universe physics signatures where Planck scale effects were more relevant. The cosmic microwave background carries information from when the universe was very young and much denser. Patterns in that radiation might encode traces of pre-spacetime physics, though identifying such traces is extremely difficult. Gravitational wave astronomy opens new windows on strong gravity phenomena. LIGO and Virgo detectors observe merging black holes and neutron stars, and future space-based detectors like LISA will probe longer wavelengths. Deviations from general relativity predictions might hint at modified gravitational physics, though connecting such deviations to space-time emergence is not straightforward. Tabletop experiments testing quantum mechanics at increasingly large scales probe the boundary between quantum and classical. If space-time emerges from quantum information, signatures might appear in how quantum superpositions behave at macroscopic scales. These experiments have not revealed anything beyond standard quantum mechanics, but they continue improving. Analog systems, mimicking certain gravity and horizon features, like acoustic black holes in fluids, allow laboratory tests of concepts that cannot be tested with actual black holes. These are not tests of emergent spacetime directly, but they provide experimental handles on related theoretical ideas. Perhaps the most important tests are theoretical consistency tests. Emergent spacetime frameworks must be internally consistent, must reproduce known physics in appropriate limits, and must make novel predictions. Much current effort goes into developing frameworks to the point where such tests are possible. The situation resembles general relativity's early days, when the theory was mathematically compelling, but direct tests were scarce. Patience and ingenuity eventually provided tests. The same may happen for emergent spacetime. Common misconceptions about what spacetime not being fundamental means deserve addressing. The first misconception is that non-fundamental spacetime means reality is illusion. This is incorrect. When physicists call temperature non-fundamental, they do not mean temperature is illusion. Temperature is perfectly real, measurable, predictable, technology-enabling. It just emerges from something deeper, atom motion. Similarly, if space-time emerges from quantum information or some other structure, space-time would still be perfectly real. You would still move through 3 spatial dimensions and experience time. Predictions and observations using space-time concepts would remain valid within their domain. Emergent space-time does not mean illusory space-time. The second misconception is that ADS-CFT proves our universe is a hologram. It does not. ADS-CFT is a theoretical laboratory demonstrating how holographic emergence can work in principle. Whether our universe is holographic, whether the same principles apply to our expanding cosmos with positive cosmological constant, remains an open question. Research is promising, but not conclusive. The third misconception is that the Amplituhedron replaces space-time for all physics. It does not. The Amplituhedron applies to a specific, highly symmetric theory in a specific limit. It is proof of concept that space-time locality might be derived rather than fundamental, not a general replacement for space-time in the Standard Model or general relativity. The fourth misconception is that these ideas are fringe or speculative in a dismissive sense. They are speculative in the sense of not being experimentally confirmed, but they are not fringe. Researchers involved include some of theoretical physics' most respected names. Work is published in top journals. Ideas are discussed at major conferences. This is mainstream theoretical physics research, even if it challenges assumptions. What researchers usually mean by saying space-time is not fundamental is that the most basic physics equations might not contain space-time as an ingredient. Space-time might be a derived quantity, extraordinarily useful, completely valid within its domain, but not the final word. Why you should care whether space-time is fundamental or emergent matters. The question determines future physics direction. If space-time is fundamental, progress means understanding space-time better, finding more complete equations describing its dynamics, unifying gravity with quantum mechanics within a space-time framework. This has been the dominant approach for decades. If space-time is emergent, progress means understanding what space-time emerges from. Fundamental questions become: what are the deeper degrees of freedom? What rules govern them? How does space-time geometry arise from those rules? This is a different research direction with different mathematical tools. The question also matters for specific puzzles. The black hole information paradox, the cosmological constant problem, and the nature of singularities all look different depending on whether space-time is fundamental or emergent. If space-time is emergent, singularities might not be genuine reality features, but artifacts of using space-time description where it breaks down. The question matters for understanding the early universe. In standard cosmology, the Big Bang is a singularity, a point where space-time itself began. If space-time is emergent, the Big Bang might not be reality's beginning, but a transition to a phase where space-time description becomes valid, with something else preceding it. The question even matters for science fiction speculation. Faster-than-light travel, wormholes, and time machines all depend on space-time properties. If space-time is emergent, these possibilities might be constrained by rules of whatever space-time emerges from, or they might be enabled by manipulating deeper structures. We do not know enough yet to say. At deeper level, the question matters for understanding what reality is. If space-time is fundamental, reality is ultimately geometric. If space-time emerges from quantum information, reality might ultimately be informational. The nature of existence itself hangs on the answer. A recurring theme in emergent space-time research is that information might be more fundamental than matter or geometry. Information, in the technical sense, concerns distinguishability. How many different states can a system occupy, and how much can observing it reveal? Bits measure information, with each bit representing a choice between two possibilities. Classical physics treats information as secondary. Particles possess positions and momenta, and information merely describes those properties. The particles are real, while information is about the particles. Quantum mechanics complicates this picture. A quantum system's state is not a list of definite properties, but a superposition of possibilities, making the state informational in nature. Measuring the system extracts information and changes the state. The holographic principle suggests information is not just a description of physics, but might be physics itself. Maximum information in a region scales with boundary area. Geometry is determined by entanglement, which is a form of quantum information. And space-time might be a way information organizes itself. John Wheeler, one of the great 20th century physicists, captured this with the phrase, "it from bit." Physical reality, the it, might arise from information, the bit, and the deepest level of existence might be made of information. Speculation this is, but mysticism it is not. Mathematical frameworks of holography, amplitudes, and quantum error correction all point toward information as central concept. If information is fundamental, many puzzles look different. The black hole information paradox becomes a question about how information encodes rather than whether it is preserved. Space-time's nature becomes a question about how information structures give rise to geometry. Physics unification becomes a question about information-theoretic principles underlying all phenomena. A complete theory built on information as fundamental does not yet exist, but hints are strong enough that this direction is being actively pursued. What does this mean for understanding our place in existence? For centuries, humans have developed intuitions about space and time. 3 dimensions of experience, time flowing from past to future, and these intuitions feel basic, built into perception and cognition. Physics history has repeatedly challenged these intuitions. Newton showed space and time had mathematical structure beyond everyday experience. Einstein showed space and time were unified with measurements depending on relative motion. Quantum mechanics showed particles do not have definite positions and momenta until measured. Each revolution required updating intuitions that felt self-evident. Each showed the world is stranger than it appears. Possible space-time emergence represents the next step in this tradition. If space-time derives from quantum information structures, then everyday categories of location, distance, and duration are not the most fundamental reality descriptions, but effective descriptions, useful approximations breaking down at extremes. Humans developed mathematics and experiments capable of revealing this, which itself is remarkable. Our brains evolved for survival on African savannas, not for understanding quantum gravity. Yet, here we are, using abstract mathematical reasoning to probe questions our perceptual systems cannot directly access. This is the human-centered takeaway from emergent spacetime research. Not that we are insignificant, but that our capacity for abstract thought can reach beyond sensory limitations. We can deduce reality features we cannot see, hear, touch, or feel. The categories we developed, space and time, location and distance, may not be the final vocabulary. The capacity that allowed developing those categories and recognizing their limitations points toward deeper understanding yet to come. Going deeper into the ADS-CFT correspondence helps clarify what space-time emergence might mean. Anti-de Sitter space solves Einstein's equations with negative cosmological constant. Unlike our expanding universe, ADS possesses a characteristic length scale and a boundary at spatial infinity, which is not a physical wall, but a mathematical surface where geometry approaches a specific limit. Five-dimensional ADS space has a four-dimensional boundary. Four-dimensional ADS space has a three-dimensional boundary. Each case shows the boundary possessing one fewer dimension than the bulk. The conformal field theory on the boundary is a quantum field theory with special conformal symmetry, relating physics at different scales. The theory has no gravity, living on a fixed background rather than dynamical space-time. Yet this boundary theory, through the ADS-CFT correspondence, contains all bulk gravitational theory information. Every bulk gravitational phenomenon, every black hole, every curvature fluctuation, every particle moving through bulk space-time corresponds to something calculable in the boundary theory. The boundary theory has no bulk dimension, yet from the pattern of boundary correlations, you can reconstruct entire bulk space-time. The extra dimension emerges from boundary physics. How does a dimension emerge? The rough answer involves the renormalization group, the physics of how systems look different at different scales. Boundary theory physics at different energy scales corresponds to physics at different bulk radial positions. High boundary energy corresponds to deep in the bulk. Low energy corresponds to near the boundary. Renormalization group flow, the connection between different scales, becomes geometrized as motion along the radial direction. This is not mathematical trick, but exact duality. Calculations hard in boundary theory can be easy in bulk and vice versa. The two descriptions are genuinely equivalent, not approximations of each other. If you accept the correspondence, bulk space-time with its dimension, gravity and geometry is not fundamental, but a rewriting of boundary physics in geometric language. Space-time emerges. Gerard 't Hooft and Leonard Susskind, two physicists who developed the holographic principle before Maldacena's precise formulation, deserve attention here. Gerard 't Hooft, a Dutch physicist sharing the 1999 Nobel Prize for electroweak interaction work, is one of theoretical physics' deepest thinkers, known for technical brilliance and conceptual insight. In 1993, 't Hooft proposed dimensional reduction in quantum gravity, arguing that gravitational theory degrees of freedom do not fill up a volume but live on surfaces. Black hole thermodynamics motivated this idea, where entropy scales with horizon area. If information about what falls into a black hole lives on the horizon, perhaps information about any region lives on its boundary. Leonard Susskind, an American physicist at Stanford, has made foundational contributions to string theory and quantum gravity. He is known for developing string theory's modern formulation and for decades of black hole and information work. Susskind took 't Hooft's idea and developed it into the holographic principle in the mid-1990s, coining the evocative phrase that the world might be a hologram, meaning three-dimensional reality might encode on a two-dimensional surface. Suskind's black hole work led him to black hole complementarity, the idea that different observers see different black hole physics descriptions that are both valid within their domains. An observer falling into a black hole experiences different physics than an observer watching from outside, and both descriptions are correct. In 2013, Susskind collaborated with Maldacena on the ER equals EPR conjecture, connecting his long black hole work with quantum entanglement. The conjecture unifies wormhole ideas Susskind had studied for years, with entanglement ideas running throughout quantum information theory. Both 't Hooft and Susskind were thinking about emergent spacetime before tools existed to make ideas precise. Their intuitions shaped the field and laid groundwork for developments that followed. Explaining entanglement more carefully matters because it is central to emergent spacetime ideas. Entanglement is a quantum phenomenon with no classical analog. When two quantum systems become entangled, their states correlate in ways that cannot be explained by any local hidden information each system carries independently. The classic example involves two particles created together, each with a property called spin that can be measured as up or down. In an entangled state, neither particle has definite spin until measured. Measurements are perfectly correlated though. Measuring one particle and finding spin up means the other particle, when measured, will always show spin down. Einstein found this disturbing. It seemed like measuring one particle instantly affected the other, no matter how far apart they were. He called it spooky action at a distance. No actual action or signal is sent, though. The correlation is simply there, built into the quantum state from the start. Entanglement entropy measures entanglement. A quantum system divided into two parts has entanglement entropy, telling you how correlated the two parts are. A product state, where each part is independent, has zero entanglement entropy. A maximally entangled state has maximum entanglement entropy. In holography, this abstract quantum information quantity becomes geometric. The Ryu-Takayanagi formula says boundary region entanglement entropy equals a specific bulk surface area. More entanglement means more area. Changing entanglement changes geometry. This suggests space-time fabric. The geometry determining distances and curvature is woven from entanglement. Threads holding space-time together are quantum correlations. Reducing entanglement stretches geometry. Removing entanglement entirely tears space-time. Space connectivity is not a given, but a consequence of quantum information structure. This is one of theoretical physics' most remarkable ideas. Space itself might be a derived property of how quantum information organizes. Conformal field theory deserves more careful explanation, because understanding what lives on the boundary clarifies what emergence means. A conformal field theory, or CFT, is a quantum field theory possessing conformal symmetry. This symmetry includes usual space-time symmetries, translations, rotations, and Lorentz boosts, but also includes scale transformations and special conformal transformations. Scale symmetry means physics looks the same at all scales. Zoom in or zoom out, and the theory has the same form. This is unusual, since most physical systems have characteristic scales. Atoms have size. Light wavelengths have specific values, and temperatures have meaning. A conformally invariant theory has no such built-in scales. The CFT appearing in ADS-CFT is typically a gauge theory, similar in structure to theories describing the strong and electro-weak forces in the Standard Model. In the most studied example, the CFT is a theory with maximum supersymmetry called n=4 super-Yang-Mills theory. This is not a real-world description, but a precisely defined theory that can be studied exactly in certain limits. The CFT lives on the ADS space boundary. This boundary is a lower-dimensional manifold. For 5-dimensional ADS, the boundary is 4-dimensional. The CFT has no bulk, no extra dimension to explore. It is defined entirely in terms of boundary degrees of freedom. Yet, from this boundary CFT, entire 5-dimensional bulk space-time with gravity emerges. Bulk geometry, particle motion through the bulk, black hole formation and evaporation all can be computed from CFT correlators. The mapping between bulk and boundary is called the holographic dictionary. It specifies how bulk quantities translate to boundary quantities. Bulk fields correspond to boundary operators. Bulk particle masses correspond to boundary operator dimensions. Bulk geometry corresponds to boundary entanglement. The dictionary is not simple. Translating between bulk and boundary is often technically difficult. The dictionary's existence is the key point, though. Everything in the bulk has a boundary description. The bulk is fully encoded on the boundary. The contrast between traditional Feynman diagram calculations and the Amplituhedron approach illustrates what locality being emergent might mean. Traditional approach computes scattering amplitudes by drawing all possible Feynman diagrams. Each diagram represents particles propagating through spacetime, meeting at vertices where interactions happen, propagating away. Mathematical expressions get assigned to each diagram, and summing them all gives the answer. Diagram rules encode space-time locality. Each vertex happens at a point. Particles travel from point to point. Total answer builds from local ingredients. Simple processes work well with this approach. Complex processes involving many particles cause diagram number to explode. Processes with many external particles might require millions or billions of diagrams, each contributing a small amount to the total. What physicists discovered, gradually over decades, is that adding up all those diagrams produces massive cancellations. Terms that seem essential individually cancel against other terms. The final answer is much simpler than intermediate calculations suggest. This is suspicious. If space-time locality were truly fundamental, why would local contributions cancel so dramatically? Why would the final answer, the measurable probability, be simpler than the sum of local histories? The Amplituhedron provides potential explanation. The scattering amplitude is not really a sum over local histories, but more directly a geometric quantity, the canonical form of a shape in abstract space. Feynman diagram expansion is one way to compute this quantity, a way using locality as crutch. The quantity itself does not require locality, though. This is analogous to computing a circle's circumference. You could approximate it by summing many straight line segments, with more segments getting you closer. The circumference is not fundamentally made of straight lines, though. It is a property of the circle itself. Line segments are computational tools, not underlying reality. In this view, space-time locality is a computational tool. The fundamental quantity is geometric, and locality emerges when you expand that quantity in a particular basis. The emergence of space-time connects to the broader quest for quantum gravity, the unification of quantum mechanics and general relativity. String theory was the first framework seriously suggesting space-time emergence. String theory's fundamental objects are not point particles, but one-dimensional strings. Space-time geometry emerges from string dynamics. Different string configurations correspond to different space-time backgrounds. The ADS-CFT correspondence emerged from string theory and provides the clearest space-time emergence example. Loop quantum gravity takes a different approach. It quantizes space-time geometry directly, proposing space is made of discrete chunks called spin networks, with space-time built from these chunks evolving in time. In loop quantum gravity, space-time is not continuous at Planck scale, but has granular structure. This is a form of space-time emergence, though different from the holographic version. Causal set theory proposes space-time is fundamentally discrete, a collection of events with causal relations between them. Continuous space-time emerges when event number becomes large. This approach takes causal structure as fundamental and derives geometry from it. Causal dynamical triangulations build space-time. From simple building blocks like triangles in 2 dimensions or their higher dimensional analogues. Summing over all assembly ways recovers space-time as emergent structure. The approach has had success reproducing 4-dimensional space-time from purely discrete ingredients. What these approaches share is the idea that continuous space-time is not the starting point. Something more basic, strings, spin networks, discrete events, or triangulations, gives rise to observed space-time. Details differ, but the emergence theme is common. Evidence from holography and amplitudes adds weight to this theme. Multiple independent research lines point towards space-time as derived rather than fundamental. No single approach has been proven correct, but convergence is suggestive. Returning to what fundamental means shapes how we interpret these ideas. In one sense, fundamental means appearing in basic equations. If the most precise equations we can write do not contain space-time as ingredient, then space-time is not fundamental in this sense. It is derived, like temperature or pressure. Another sense of fundamental exists, though: fundamental to explanation. Even if space-time is derived, it might be the right description level for understanding most phenomena. You could, in principle, describe weather in terms of atoms, but that would be absurd. Weather is better explained using pressure, temperature, and humidity, which are not fundamental, but are the right concepts for the job. Space-time might work similarly. Even if deeper equations do not contain space-time, we might continue using space-time for most physics because it is the right description level for the phenomena we want to explain. This distinction matters for interpreting emergent space-time research. The claim is not that space-time should be abandoned. The claim is that understanding reality's deepest structure might require going beneath space-time, just as understanding thermodynamics requires going beneath temperature to underlying microstates. Practical consequences would depend on what questions you ask. Building bridges, launching rockets, or designing microchips would use space-time as the right framework. Understanding black hole interiors, the very early universe, or gravity and quantum mechanics unification would use deeper structure. Physics often works this way. Different frameworks suit different questions. Newtonian mechanics is not wrong, but is appropriate for everyday speeds and scales. Relativity becomes necessary at high speeds. Quantum mechanics becomes necessary at small scales. Frameworks are not contradictory, but appropriate in different regimes. If space-time is emergent, space-time physics would be appropriate for ordinary scales, and deeper information-based structure would become relevant only at extreme conditions like Planck Scale or inside black holes. Historical parallels offer instructive lessons for what might happen with space-time. Consider the ether. In the 19th century, physicists believed light waves, like all waves, required a medium to propagate through. This medium was called luminiferous ether, supposed to fill all space, provide absolute reference frame, and carry electromagnetic waves. The Michelson-Morley experiment in 1887 failed to detect ether effects. Einstein's special relativity in 1905 eliminated need for it. Ether went from fundamental physics ingredient to discarded concept within 20 years. Was space-time the next ether? In some sense, yes. Einstein's space-time replaced ether as the physics arena. Space-time itself might now be headed for demotion, not as wrong, but as derivative. Consider phlogiston. In the 18th century, chemists believed burning released a substance called phlogiston, explaining why things became lighter when burned and why metals calcified. Lavoisier's discovery of oxygen made phlogiston unnecessary. Burning was not phlogiston release, but oxygen combination. The parallel here is that concepts seeming necessary for explanation can be replaced by better concepts. What seemed like fundamental ingredients turn out to be bookkeeping artifacts of incomplete frameworks. Consider the atom. For centuries, atoms were thought to be smallest, indivisible matter units. Physicists discovered atoms have internal structure: electrons, protons, neutrons. Protons and neutrons turned out to be made of quarks. Each generation's fundamental became the next generation's composite. The pattern suggests caution about declaring anything truly fundamental. Today's bedrock might be tomorrow's emergent phenomenon. Space-time, seeming so basic to Einstein's physics, might follow the same trajectory. This does not diminish physics achievements based on space-time. Special and general relativity remain extraordinarily successful theories, correctly predicting countless phenomena. They might not be the final word, though. Describing anti-de Sitter space more carefully helps clarify why it is useful for studying emergent spacetime. Anti-de Sitter space, or ADS, solves Einstein's equations with negative cosmological constant. The cosmological constant is a term Einstein added to his equations, acting like uniform energy density throughout space. Positive cosmological constant causes spacetime to expand. Negative cosmological constant causes spacetime to contract. ADS has characteristic length scale set by cosmological constant. The geometry is curved everywhere, with negative curvature like a saddle surface, generalized to higher dimensions. Unlike flat space extending infinitely in all directions, ADS has a boundary at spatial infinity. This boundary is unusual. In flat space, spatial infinity is just the limit of going farther and farther away, with nothing special happening there. In ADS, spatial infinity is a genuine boundary, a surface where geometry behaves in specific way. 5-dimensional. ADS boundary is 4-dimensional, like everyday spacetime, but without extra bulk dimension. 4-dimensional ADS boundary is 3-dimensional. In general, the boundary has one fewer spatial dimension than the bulk. The special property making ADS useful for holography is that information can propagate to boundary and back in finite time. The geometry funnels everything toward the boundary, allowing precise relationship between bulk and boundary physics. Our universe is not anti-de Sitter. We have positive cosmological constant, and our space-time is expanding. De Sitter space with positive cosmological constant has different properties. Generalizing holography from ADS to de Sitter, which would be more relevant for our universe, is an active research problem that has not been solved. ADS-CFT works as well as it does partly because of ADS's special geometric properties. Whether similar correspondences hold for more realistic spacetimes remains an open question. ADS provides the proof of concept that spacetime emergence is possible, though. The Bekenstein-Hawking formula deserves more concrete development with numbers. The formula tells us black hole entropy is proportional to event horizon area. In Planck units, entropy is 1/4 of area measured in Planck areas. A Planck area is Planck length squared, approximately 2.61 times 10 to the negative 70 square meters. This is an inconceivably tiny surface patch. Consider a region with 1 square meter surface area, about 10.76 square feet. How many Planck areas fit on this surface? Roughly 3.8 times 10 to the 69 Planck areas. Using Bekenstein-Hawking scaling, this corresponds to about 1.38 times 10 to the 69 bits of information, or about 1.28 times 10 to the 68 bits per square foot. These numbers are enormous. A bit can be stored in various ways: magnetic domain orientation, electron presence or absence, photon polarization. Information capacity, suggested by Holographic Principle, vastly exceeds anything we can currently store. The point is not practical storage, but scaling. In ordinary three-dimensional intuition, information capacity should scale with volume. Double volume, double information capacity. The holographic principle says maximum information scales with area instead. This has consequences for thinking about region interiors. If information scales with area, then a region's interior does not hold more information than its boundary. The bulk, in some sense, is redundant. Everything happening inside can be described by what happens on the surface. This is counterintuitive. We feel like we live in 3 dimensions, not on a 2-dimensional surface. We move through bulk space. How can the bulk be redundant? The answer in holographic framework is that bulk space experience is itself derived from boundary physics. The feeling of moving through 3 dimensions is an effective description emerging from more fundamental boundary degrees of freedom. The bulk is real in the sense that it correctly describes experience, but it is not fundamental in the sense that it can be reconstructed from boundary data. I want to share how I came to appreciate the depth of these ideas. The first time I saw the Ryu Takayanagi idea, reading it multiple times became necessary. Entanglement, something sounding like pure information, something measuring correlations between quantum states, showing up as geometry, as surface areas in curved space-time. The two concepts seemed utterly different, yet mathematics said they were the same. There is a moment where you realize Planck scale is not just small. It is where measuring threatens to erase the very meaning of distance. You try to measure something, and the energy required for that measurement collapses the region into a black hole. The concept you wanted to define, distance below Planck length, becomes operationally meaningless. The Amplituhedron work feels like someone finding a hidden trapdoor. Answers for particle collisions, which everyone calculated using spacetime locality and Feynman diagrams for 70 years, can come from geometry, in a space that is not ordinary spacetime at all. Same numbers emerge from completely different starting points. These ideas do not fit neatly into everyday intuitions. They require holding multiple perspectives simultaneously, sometimes thinking of space-time as fundamental, sometimes thinking of it as emergent, depending on which questions you ask. This is uncomfortable. Physics history suggests discomfort often precedes progress, though. What strikes me most is how information keeps appearing as fundamental concept. Black hole entropy encodes information. Entanglement carries information. Quantum error correction protects information. The Amplituhedron encodes information about scattering. Everywhere you look in cutting-edge theoretical physics, information structures appear. Perhaps the deepest reality level is not made of particles or fields or strings. Perhaps it is made of something more abstract, patterns of information from which everything else, including space-time, emerges. Giving a sense of the scales involved helps ground these discussions, because numbers help ground ideas. Planck length is approximately 1.616 times 10 to the negative 35 meters, about 6.36 times 10 to the negative 34 inches. This is so small, it defies direct comparison to anything in everyday experience. Consider this progression. A meter is roughly desk height. A millimeter, 1/1000th of a meter, is about pinhead width. A micrometer, 1/1,000,000th of a meter, is bacteria scale. A nanometer, 1/1,000,000th of a meter, is individual molecule scale. A femtometer, 10 to the negative 15 meters, is atomic nuclei scale. Planck length is 20 orders of magnitude smaller than a femtometer. Starting at a meter and taking one step towards smaller scales, each time you move down 3 orders of magnitude, you would need almost 12 steps to reach the nucleus. You would need 12 more steps, almost 24 total, to reach Planck scale. Planck time is approximately 5.391 times 10 to the negative 44 seconds. The time light needs to travel 1 Planck length. In the universe's age, roughly 14 billion years, there are about 4 times 10 to the 60 Planck times. The ratio of cosmic to Planck timescales is about 60 orders of magnitude. At Planck scale, quantum effects and gravitational effects become equally important. Neither quantum field theory nor general relativity alone can describe physics adequately. Whatever replaces them must handle both simultaneously. Concepts we are discussing, space-time emergence, the role of entanglement, and the breakdown of locality, are all expected to become relevant at or near this scale. This is far beyond current experimental reach. We cannot probe distances anywhere near Planck length. Ideas we are discussing are theoretical, informed by mathematics and consistency arguments, not direct observation. Theoretical reasoning has often preceded experimental confirmation in physics, though. General relativity was developed decades before its most stringent tests. Quarks were predicted before they were indirectly observed. The theoretical evidence for emergent spacetime is strong enough that many physicists take it seriously, even without direct experimental proof. In 2015 and 2016, another puzzle piece fell into place. Researchers discovered holography, The emergence of bulk spacetime from boundary physics can be understood using quantum error correction language. Ahmed Almeri, Zi Dong, and Daniel Harlow, along with Fernando Pastovsky and colleagues, showed aspects of ADS-CFT correspondence look exactly like quantum error correcting codes. These are mathematical structures used in quantum computing to protect quantum information from errors. A quantum error correcting code takes some quantum information piece and spreads it across multiple physical systems, so the original information can be recovered even if some systems are damaged. The information is encoded redundantly, not in any single location, but in correlations among many locations. In holography, bulk information encodes on the boundary in analogous way. A point deep in the bulk does not correspond to any single boundary point, but to a complex boundary data pattern. You can reconstruct what is happening at a bulk point from boundary data, but mapping is non-local and redundant. This perspective strengthens the geometry from information intuition. Space-time geometry is not just emergent from entanglement, but emergent in the specific way error-correcting codes are structured. The bulk is a kind of encoded message, with encoding determined by quantum information principles. The error correction perspective also clarifies how information can fall into a black hole and still be recoverable from boundary data. Information is not lost, but encoded in increasingly complex correlations as black hole forms and evaporates. This touches on the famous black hole information paradox, one of theoretical physics' deepest puzzles. What these developments suggest is that space-time emergence is not just a vague philosophical idea. It has specific mathematical structure. Space-time emerges according to rules quantum information theory can describe precisely. The more physicists study these connections, the more it seems quantum information is not just one physics aspect, but might be the foundation from which geometry itself is built. The journey from Newton's absolute space to possibly emergent space-time spans over 3 centuries of physics. Each step required abandoning intuitions that seemed self-evident. Newton's contemporaries found gravity acting at a distance absurd. How could the sun pull on the Earth without anything between them? Yet mathematics worked, and predictions matched observations. Einstein's contemporaries found space and time unification strange. How could time depend on motion? How could simultaneity be relative? Yet mathematics worked, and predictions matched observations. Today, the idea that space-time itself might derive from something deeper seems strange to us. How can physics arena not be fundamental? How can space and time emerge from information? Yet mathematics is working, and where we can check, predictions match. Perhaps our discomfort with emergent space-time says more about intuitions than about reality. Intuitions evolved for survival, not fundamental physics. Existence is not obligated to fit evolved expectations. What is remarkable is that humans can push past intuitions. Using mathematics and careful reasoning, we can probe questions senses cannot reach. We can deduce reality features at scales 35 orders of magnitude below what we can see. Whether space-time ultimately proves fundamental or emergent, the capacity to ask the question and pursue the answer is itself extraordinary. Why these questions matter extends beyond abstract theoretical interest. If space-time is emergent, many practical questions in physics change character. The nature of black hole interiors, currently described as singularities where space-time curvature becomes infinite, might look entirely different. Singularities might not be genuine reality features, but artifacts of using space-time description where it breaks down, like trying to describe water waves using equations that assume water is continuous rather than made of molecules. The early universe poses similar questions. Standard cosmology describes the Big Bang as a singularity, a point where space-time itself began. If space-time is emergent, the Big Bang might not represent reality's beginning, but rather a transition to a phase where space-time description becomes valid. Something else might precede it, something not describable in space-time terms. Understanding the vacuum energy problem, sometimes called the cosmological constant problem, might require emergent space-time thinking. Quantum field theory predicts vacuum should have enormous energy density, yet observations show it is nearly zero. This discrepancy, often cited as physics' worst prediction, might find resolution in frameworks where space-time and energy relate differently at fundamental level. Practical technologies remain distant, but history shows abstract understanding eventually connects to applications. Einstein's relativity seemed purely theoretical in 1905, yet GPS satellites today require relativistic corrections to maintain accuracy. Quantum mechanics seemed purely philosophical in the 1920s, yet modern electronics, lasers, and medical imaging all depend on quantum effects. If space-time emerges from quantum information, understanding that emergence might eventually enable technologies we cannot currently imagine. Manipulating the deeper structures from which space-time arises might permit possibilities that seem like science fiction today. The timeline for such developments, if they ever occur, stretches far into the future. What we have now is the beginning of understanding, glimpse that space-time might not be what we thought it was. Understanding why information appears so central to these developments illuminates the research direction. Classical physics treats information as secondary, a description of physical systems rather than a fundamental element. Particles have positions and momenta, and information describes those properties. The particles are primary. Information is derivative. Quantum mechanics began shifting this perspective. Quantum states are not lists of definite properties, but superpositions of possibilities, making states informational in nature. Measurement extracts information and changes the state. The information is not just description, but participant. The holographic principle pushed further. Maximum information in a region scales with boundary area, not volume. This suggests information is not just describing physics, but constraining it at fundamental level. Black hole thermodynamics showed that entropy, an information measure, determines black hole properties. The Bekenstein-Hawking formula connects information directly to geometry through area. Ryu Takayanagi connected entanglement entropy to geometric areas, making the information geometry link precise within ADS-CFT. Geometry is not just correlated with information, but determined by it. Quantum error correction in holography showed bulk reconstruction follows information theoretic principles. The rules governing how information is encoded are the rules determining how geometry emerges. The Amplituhedron showed scattering amplitudes emerge from abstract geometric structures, bypassing space-time locality. The information about physical processes lives in mathematical structures that do not presuppose space-time. Across all these developments, information moves from description to foundation. The pattern is consistent enough that taking it seriously seems warranted. Physics at its deepest level might be about information organization, with space-time emerging as a consequence. This possibility guides active research programs at leading institutions. Whether it proves correct remains to be seen, but the direction has proved productive, generating new tools and insights, even as foundational questions remain open. The interconnection between these research threads reveals a consistent picture. Holography shows bulk space-time can emerge from boundary physics. Entanglement, geometry connections show quantum correlations determine geometric properties. Error correction shows emergence follows information theoretic rules. The Amplituhedron shows physical quantities can be computed without space-time as starting point. Each thread developed independently, yet they converge on similar conclusions. Space-time may be derived rather than fundamental. Information may be more basic than geometry. The ordinary concepts of space, time, and locality may emerge from deeper structures. This convergence is striking. Multiple research programs using different methods and addressing different questions arrive at related insights. When independent approaches agree, the underlying truth often lies somewhere in their intersection. The situation resembles earlier moments in physics history. Before quantum mechanics unified the wave and particle pictures of light, multiple lines of evidence pointed towards something strange about photon behavior. Before general relativity unified gravity and geometry, multiple puzzles suggested Newtonian gravity was incomplete. We may be at a similar moment regarding space-time. The puzzles are accumulating. The hints are becoming clearer. A unified understanding may be approaching, though what form it will take remains uncertain. What makes this moment in physics special is the convergence of theoretical tools. We have holography from string theory, amplitude methods from particle physics, quantum information from computer science, and tensor networks from condensed matter physics. These fields are cross-pollinating, generating new ideas neither could have produced alone. The next decade may bring breakthroughs we cannot anticipate, or it may reveal that the puzzles are even deeper than currently imagined. Either outcome would advance understanding. Understanding the hierarchy of scales in nature reveals just how far beyond everyday experience these space-time questions reach. Human bodies measure roughly 1 to 2 meters tall. Bacteria span a few micrometers, about 1 million times smaller than human scale. Atoms measure about an angstrom, 10,000 times smaller than bacteria. Atomic nuclei span about a femtometer, 100,000 times smaller than atoms. These scales span about 15 orders of magnitude from human to nuclear. Each step down reveals new physics. Biology gives way to chemistry, chemistry to atomic physics to nuclear physics. Different concepts become relevant at each scale. Planck length sits another 20 orders of magnitude below nuclear scale. The step from nuclear to Planck exceeds the step from human to nuclear. Journeying from familiar scales to Planck scale crosses 35 orders of magnitude. Each historical step down changed physics' character. What physics looks like at Planck scale, where emergent space-time ideas become relevant, remains unknown. Theoretical frameworks exist, but direct observation does not. Timescales tell a parallel story. Human heartbeats take about a second. Atomic processes happen in attoseconds, around 10 to the negative 18 seconds. Nuclear processes happen in femtoseconds to attoseconds. Planck time sits at 10 to the negative 44 seconds, roughly 26 orders of magnitude below atomic timescales. The universe's age of about 14 billion years, roughly 4 times 10 to the 17 seconds, spans 61 orders of magnitude above Planck time. That range from Planck time to cosmic age is staggering. Energy scales follow similar patterns. Room temperature corresponds to about 0.025 electron volts. Chemical bonds involve a few electron volts. Nuclear physics involves mega-electron volts. Planck energy reaches about 10 to the 19 giga-electron volts, or 10 to the 28 electron volts. At Planck energy, gravity becomes as strong as other forces. Quantum gravitational effects become unavoidable. Emergence of space-time, if it occurs, happens around these scales. What we are discussing touches the foundations of existence. The questions are deep, the evidence is theoretical, and the answers remain elusive. Yet the patterns emerging from holography, from amplitude physics, from quantum information, all point in similar directions. Space-time may not be the bedrock we thought it was. The stage on which physics plays might itself be part of the performance, emerging from something we do not yet fully understand. That possibility drives some of the most brilliant minds in physics to keep pushing at these questions. Whatever they discover will reshape our understanding of space, time, and reality itself. The journey from Newton's absolute space to possibly emergent space-time spans over 3 centuries of physics, with each step requiring abandonment of intuitions that seemed self-evident. Newton's contemporaries found gravity acting at a distance absurd. How could the sun pull on the Earth without anything between them? Yet the mathematics worked, and predictions matched observations. Einstein's contemporaries found space and time unification strange. How could time depend on motion? How could simultaneity be relative? Yet the mathematics worked, and predictions matched observations. Today, the idea that space-time itself might derive from something deeper seems strange to us. How can the arena for physics not be fundamental? How can space and time emerge from information. Yet, the mathematics is working, and where we can check, predictions match. Perhaps our discomfort with emergent space-time reveals more about our intuitions than about reality. Intuitions evolved for survival, not for fundamental physics. And existence is not obligated to fit evolved expectations. What is remarkable is that humans can push past these intuitions. Using mathematics and careful reasoning, we can probe questions our senses cannot reach, deducing reality features at scales 35 orders of magnitude below what we can see. Where this research leads, and what a complete theory would look like if space-time is not fundamental, remains honestly unknown. Research programs we have discussed, holography, the Amplituhedron, and entanglement geometry connections, are puzzle pieces not yet assembled. Each piece suggests something about the final picture's shape, but none is the complete picture itself. One possibility is that the fundamental theory is defined in terms of quantum information, with basic degrees of freedom being quantum bits, organized according to specific rules. Space-time would emerge from entanglement patterns among these bits, the way a hologram emerges from interference patterns on film. Another possibility is that the fundamental theory is defined in terms of abstract mathematical structures like positive geometries associated with the Amplituhedron. Scattering amplitudes and perhaps other physical quantities would be computed from these structures without space-time locality reference. Space-time would emerge as a derived property of how these quantities organize. A third possibility is that space-time is fundamental in some sense not yet grasped. Hints of emergence might be artifacts of studying special cases like ADS space or highly symmetric theories. Full picture understanding might reveal space-time as basic after all, just in different form than currently conceived. Research continues. Positive geometry methods are extending beyond the original Amplituhedron. Holographic ideas are being applied to more realistic settings. Quantum information concepts are integrating more deeply into theoretical physics. What seems clear is that the 20th century framework, with space-time as fundamental physics arena, is being reconsidered. Whether space-time ultimately remains fundamental in revised sense, or gets replaced by something deeper, the reconsidering process has already yielded new insights and new tools. The next breakthrough might clarify the picture entirely, or it might reveal the puzzle as even more complex than currently imagined. Either way, exploration continues. Let me bring this exploration to a close. We have traveled from Newton's absolute space through Einstein's dynamic space-time to the possibility that space-time itself emerges from something deeper. Black hole thermodynamics suggested information scales with area. The holographic principle proposed bulk physics encodes on boundaries. ADS-CFT provided a concrete laboratory where space-time demonstrably emerges from boundary physics. We explored the Ryu-Takayanagi formula, tying geometry to entanglement. We considered Van Ramsdonk's argument that entanglement holds space-time together. We encountered the ER equals EPR conjecture, linking wormholes and quantum correlations. We saw how the Amplituhedron suggests even locality, the idea that interactions happen at points might be derived rather than fundamental. None of this is proven in the sense of experimental confirmation. What exists is theoretical evidence, mathematical frameworks working too well to be coincidences, patterns suggesting deep connections between geometry and quantum information, and serious research programs pursued by leading physicists. If spacetime is emergent, what does that mean for you, standing on Earth, looking up at the stars? It means the space separating you from those stars might not be the most fundamental reality description. Distances you experience and time that flows as you wait might be derived quantities, extraordinarily accurate within their domain, but not the deepest description level. It means human curiosity, mathematical reasoning, have probed beneath intuitions evolution gave us. We evolved to understand space and time at human scales, but our minds can reach beyond those scales, deducing reality features our senses cannot directly access. It also means the story is not over. The deepest understanding of space, time, and reality remains to be discovered. Researchers working on these questions are pushing the boundaries of human knowledge, and what they find will shape physics for generations to come. Thank you for taking this journey with me through ideas that challenge our most basic assumptions about reality's nature. If you found value in this exploration, consider subscribing. It helps these deep dives reach more curious minds. Sleep well tonight, resting in a space-time that may or may not be fundamental. Good night.